This video details a framework for open source clinical trial reporting. It is motivated by the question of whether or not we can report clinical trials using open source software, and if so, what would a solution look like? Welcome to this presentation. My name is Chris Rook, and I'm a consultant statistical programmer. This is part 3 of an end-to-end framework for clinical trial reporting using open sources. The focus here is on a graphical sandbox for ad hoc reporting, a full working prototype that includes 12 distinct interactive figure types will be presented. The data we will use is generated with R, and the sandbox code is written in Python, and the interfaces are enclosed within a Jupyter notebook. This graphical sandbox can be delivered to the clinical team along with other internal customers, and it allows for exploration of the data. The figures produced can be saved, however, they will automatically be marked as draft until validated and approved by the Biometrics and Data Sciences team. All figure code is written in Python, and the user interfaces presented can be produced by statistical programmers. If built using classes, a library of such interactive figures can be saved for reuse across studies. This effort will include line plots, Edish plots, liver function plots, AE dot plots, swimmer plots, waterfall plots, survival plots, line, bar, and forest plots, box plots, spaghetti plots, scatter plots, and panel by scatter plots. The strategy in this presentation is to discuss each of the 12 figure types, highlighting features of both the interface and code. We will detail how the standard interface was constructed, including the creation of classes to hold collections of related controls for easy reuse. A short demonstration of each figure will be provided along with ideas for future enhancements. We will now generate some data, then present the graphical sandbox. This R program will create completely synthetic ADSL, ADAE, ADLB, ADVS, and ADTTE datasets as JSON files, which will be read by Python and saved as pickle files, which have a .pkl extension. Since Pandas data frames do not allow column labels, we will generate 2 versions of these datasets. One version will contain variable names of 8 characters or less that abide by the rules of SAS version 5 transport files. When using these data frames, the variable labels are stored and accessed separately in a Python dictionary. The second set of data frames has column labels as variable names. When using these data frames, we do not need to store and access the labels separately. We start with simple line plots plus minus standard error bars, which have three drop-down controls that allow the user to select the data frame, the parameter, and the variable to plot. A button control allows the user to save the displayed line plot to a file. Next is an Edish plot for parameters having normal ranges. Drop-down controls are used to select the data frame along with the x-axis and y-axis variables, which are ratios to ULN. Text box controls are used to set reference lines and for labeling the four quadrants. Lastly, there is a button control to save the current Edish plot as an external file. The liver function plot uses drop-down boxes for selecting the data frame and subject to plot, along with radio buttons for the population, and a multi-select control for choosing which parameters to display. Drop-down boxes allow only one selection, whereas multi-select controls allow many. Lastly, there is a button control to save this liver function plot to a file. The adverse event dot plot uses a drop-down box for selecting the data frame and an integer slider control for selecting the common AE threshold %. Radio buttons are used for filtering by AE action taken, and checkboxes are used for filtering by AE outcome. The user iterates through pages using a text box control, and there is a button to save the current AE dot plot to a file. The swimmer plot displays one treatment at a time and allows the user to select that treatment via a drop-down box. An integer slider is used to control how many subjects are displayed per page, whereas a combination of drop-down box and multi-select controls are used for filtering. Button and text controls allow the user to iterate through pages. And lastly, both the figure and reporting data frame can be saved to various file formats using the button and drop-down box controls at the bottom. The waterfall plot contains a series of drop-down boxes that allow the user to select a data frame, parameter, plot variable, group by or color variable, and page by variable. Radio buttons are used to set the population and statistic to present, and a collection of drop-down box and text controls are used for filtering. All active filters will be displayed in the footnote. There are also options to add reference lines and annotations, which are markers to identify subjects meeting a specific condition. Lastly, paging and saving controls allow the user to save the plot, and a file name is suggested based on the options selected. Survival plots position controls on the left to make efficient use of screen space. They contain a drop-down box for selecting the parameter to analyze, and checkbox controls for adding plot-specific features such as the number of subjects at risk and with events. Populations and plot type are selected using radio buttons, whereas drop-down and multi-select controls are used for filtering. There is also a set of controls with various options for saving the survival plot as a file. The MMRM line, bar, and forest plots reveal what is to become the standard interface. Drop-down boxes allow selection of the data frame, parameter, and page by variable, and the population is selected with radio buttons. Filtering is done as usual with a collection of drop-down and multi-select boxes. Page viewing is controlled using drop-down boxes, buttons, checkboxes, and float slider controls. Another collection of controls will allow the user to save both the figure and data used to generate it to external files. Lastly, there is a plot-specific set of controls which here allow the user to select plot type, define responses, and set both categorical and continuous covariates for the repeated measures mixed model. Box plots will make use of the standard interface just discussed by reusing the separate collections of controls for 1. Selecting data and parameters, 2. Filtering the data, 3. Paging the figure, and 4. Saving both the data and figure to external files. The only difference here is with the plot-specific set of controls in the middle. Here, the box plot allows selection of an analysis variable, i.e. eval or change, and treatment grouping. Reference lines can be added along with several box plot-specific features, such as displaying means and outliers. Spaghetti plots also make use of the standard interface previously discussed. The plot-specific set of controls for a spaghetti plot includes selection of the analysis variable, i.e. eval or change, and the treatment or grouping variable, along with setting reference lines and adding subject-specific event indicators to the plot. Scatter plots make use of the standard interface, and plot-specific settings include selection of the analysis variable and treatment or group by variable. The user can set reference lines and annotate the plot with various items such as regression lines and equations and outlier IDs. Panel by scatter plots will make use of the standard interface, and plot-specific settings are similar to that of regular scatter plots just discussed, except that there is now a setting for the panel by grouping variable. As noted earlier, the standard interface makes use of classes in Python. Classes contain data and functions. An object is an instantiation of a class for a given implementation. Here, the figure input selections container is one class that contains all the controls and data needed to operate. The data filter settings collection is also a class, as are the paging controls and saving controls. A figure class then contains an instance of each, along with requirements for a plot-specific class that is passed to the figure class via its constructor when it is instantiated. Creation of a new figure for the sandbox is now relatively simple. We build a plot-specific class abiding by a few rules, then instantiate the figure class with an object of the plot-specific class. This concludes Part 3 of a framework for end-to-end clinical trial reporting using open sources. We have presented a full working prototype for a graphical sandbox with user interfaces for ad hoc reporting. My LinkedIn and email addresses are shown below. Feel free to contact me with any questions and/or concerns. Thank you for watching.